under the BSD family of operating systems. So NetBSD, OpenBSD, FreeBSD, and BSDI, which use the same memory allocator. So explaining one allocator is okay for the 4 OSs. First, I'm going to present a little overview, see the explanation of the algorithms, then really detail the algorithms, the malloc functions, etc., and present simple exploitation techniques with simple programs, simple vulnerable programs, and IDs to exploit these programs. And then we will see a real flow exploitation. So for the overview, first thing we have to know is that the BSD allocator and the BSD kernels propose 2 different memory regions. The first region is the break region. It is the first memory region that is located after the BSS of the program, which is the uninitialized data region. And the end of this region is given by the break. So the break, when the program starts, simply is a pointer to the end of the uninitialized data region. And whenever the program needs more memory, it can increase the break through the sbrk and brk calls. And when it increases the break, it can use all the memory that is located between the end of the uninitialized data region and the new position of the break. This is the first independent region of memory. And the position of the break is quite different between FreeBSD, NetBSD, and OpenBSD. Under FreeBSD, the break is located at about 0804 something. And under OpenBSD, it starts at 0000 something. So most of the time, exploits will be different for OpenBSD and FreeBSD, NetBSD, because it's very hard in general to write a 0 somewhere in memory. So it may require completely different exploitation techniques. A second memory region is the mmap region, which simply is completely independent from the brk region and is represented by files mapped into memory. So when the allocator needs some memory in the mmap region, it just has to map a file descriptor. Most of the time it is an open file descriptor to dev0, and it maps this file in memory. The kernel chooses the free memory area to map the file and returns the address to the mmap call. So the address is completely different from addresses for the brk region. So the allocator is split into 2 logical layers. The bottom layer only knows about memory pages. It only allocates and frees memory pages, complete memory pages, which are contiguous sets of data of fixed size. And the top layer handles chunks. So when the user program requires a little memory, a little zone of memory, the top layer function first relies on the bottom layer to allocate a memory page and splits the memory page in several chunks, and one of the chunks is returned to the user. This top layer also handles internal use chunks, which are used by the allocator to reference its different structures, its different memory regions, and it is the same path in the code to allocate either a user chunk or an internal use chunk. So user chunk and internal use chunks are intermixed. The user chunk may well override an internal use chunk. Now, the bottom layer to reference the memory pages first positions these pages in the brk region, and the mmap region is only used to reference the pages. The mmap region is dedicated to internal use. The user pages in the brk region are referenced in an array that is indexed with the ptr to idx macro. And this macro takes a page address and returns a unique index in the array corresponding to the page. So when you have one page, you have one position in the array, one element of the array, and this element corresponds to the page. These elements may be set to either malloc not mine, which means the corresponding page has not yet been allocated with the brk or sbrk call, and thus should not be used. it can be set to malloc first or malloc follow for contiguous set of pages that have been allocated at the same time. If I allocate 3 pages, the first element corresponding to the first page will be set to malloc first, and the 2 other elements will be set to malloc follow. And then you have malloc free, which means the page is mapped, it is in the BRK region, but it has been freed through calls to free or something. But the top layer may override these values. The top layer allocates memory from the bottom layer, and then it may override the values, use the memory, restore the value, and give the page back to the bottom layer when it becomes useless. So, how are free pages handled? They are referenced in a doubly linked list. That is a list of PG-free structures. The first field, the next is a pointer to the next element in the list. The pref field is a pointer to the previous element in the list. The page field points to the beginning of the page. The end field points to the end of the page, and the size field is the size of the page. PG-free structures may as well reference one memory page as several contiguous ones. It may reference, I don't know, 3 pages, 4 pages, any number of pages. So this will simply change the size field and the end field. The list of PG-free structures is declared as a static list, a static struct PG-free free list, and the free list has its first element is not used, only its next field is used and points to the first element of the free pages list. List elements are allocated through call to the internal memory allocator, imalloc, which is also the allocator which performs allocation for user chunks. So when I told it is exactly the same path in the code, it is the same function that is called to allocate both PG-free structures or user chunks. And one point of interest is that the list is sorted in increasing page field order. So the first element of the list is the lowest address free memory region for the bottom layer. Now the top layer makes the difference between 3 categories of chunks. First, there are large chunks that are chunks larger than half a memory page, and medium-sized and tiny chunks that are handled quite the same way. Large chunks reside in dedicated memory pages, so when a large chunk is allocated by the user, simply the top layer calls the bottom layer to allocate a full memory page or more memory pages if required, and these pages will only contain this chunk and no other chunk. Other chunks, tiny chunks and medium-sized chunks, are grouped in memory pages, and all chunks in one page have the same size. So a page only handles one category of chunk, but chunk sizes are always rounded up to a power of 2, so that there is not too much wasted space. So pages containing tiny and medium-sized chunks are referenced in linked lists. So in lists of PG info elements, these are simply linked, and the first field of the structure is a pointer to the next element of the list. The page field points to the beginning of the page. The size field contains the size in bytes of a memory chunk in this page. The shift field is simply such that size is equal to 1 shifted shift time on the left. The free field contains the number of free chunks in the page. The total field is the maximum number of chunks the page can contain. So when the free field is equal to the total field, this means that the page is empty and no chunk is used in the page. And then the bits field has in fact a variable length and references which chunks in the page are in use and which chunks in the page are free. So the lists are also sorted in increasing page field order. So the first element of the list references the page which has free chunks and which has the lowest address of the list. One list exists for each kind of page, for each kind of chunk size. So the bits field has 1 bit for each chunk in the page. The bit is set to 1 if the chunk is not in use, and is set to 0 when the chunk is free. Which bit is used for which chunk is given by a quite complicated formula. I think it's better to give an example. So on the well-known Intel architecture, you have a 32 bits word, and it is a Little Endian architecture. When no chunk is allocated, all bits of the bits field are set to 1. Then if we allocate the first chunk in the page, the lowest order bit in the lowest order word of the bits field is set to 0. If we allocate the 23rd bit in the page, the 23rd bit of the first element of the bits field is set to 0. And if we allocate the 42nd bit, the 42nd chunk in the page, then the first element of the bits field is not large enough to handle the chunk, so it will be handled by the second element, and its 10th bit will be set to 0. Other example, quite the same thing, but on big endian architecture. On big endian, when no chunk is allocated, every bit is set to 1. Then if we allocate the first bit, the lowest order bit is set to 0. 23rd chunk, 23rd bit, and 42nd chunk. Again, we need to access the second element of the bits field and set its 10th order bit to 0. So now, where are the PG infrastructures located? First, you have tiny chunks pages, and in these pages, the PG infrastructure is located at the beginning of the page. But in medium-sized chunks pages, the PG infrastructure is allocated through a call to the internal memory allocator, through imalloc, which allocates a large enough chunk and stores the PG infrastructure in the chunk. And a chunk is medium-sized if the PG infrastructure effective size, including the bits field, is less than half the size of a chunk. Also, when PG infrastructure is allocated to reference a memory page containing tiny or medium-sized chunks, an entry is created in the directory where memory pages are handled by the bottom layer, and it overwrites the value written by the bottom layer, the malloc first that was written when allocating the page. It is overwritten with the address of the PG infrastructure for the page. Now the PG phrase, it's quite more complicated. First, to store the PG phrase structures, a cache is defined as a static pointer to an array of PG phrase structures, and it is set to the address of a ready-to-use PG phrase structure or to 0. Either an available PG phrase structure has not been allocated yet, or one chunk is available to store a PG phrase structure and px is set to its address. Either no PG phrase structure is available and px is 0. So these structures are allocated through call to imalloc when px is not available, when it is empty. And when the pages become useless, either they are freed through a call to the internal memory freeing function, ifree, or if px is null, the PG phrase structure is not freed and it serves to initialize the px cache. So the precise structure of the array I was speaking about is the pages directory that is located in the mmap region. That is the only malloc structure that is located in this region, and it is declared as a pointer to an array of PG infrastructures. It is split into two different parts that serve completely different purposes. The first part of the array references the pages, the list of PG infrastructures that handle certain kind of chunks. For instance, 16 bytes chunks are referenced by the fourth element of the pages directory. So the list of pages containing three 16 bytes chunks is the fourth element of this directory. Then for 32 bytes chunks it's the fifth element, and so on. Now the second part of the pages directory is the real array that is used by the bottom layer to set proper entries to malloc first, malloc follow, malloc free, etc., and whose entries may be overwritten by the address of a PG infrastructure. What is important also is that the first elements of this array are useless because the minimum size of a chunk in this allocator is 16 bytes. A chunk cannot be less than 16 bytes, so the first four elements are not used. Now, to handle the pages directory, during malloc initialization, it is allocated through a call to the mmap function, and one memory page is allocated for the pages directory. And whenever required, when the BRK region becomes too large to be handled by simply one page of memory in the pages directory, it is extended through another call to mmap, and it is extended one page at a time. So it is accessed thanks to the ptr to idx macro, which simply divides its argument by the page size to return an index, and because pages do not start at 0, they have to shift the result, so they subtract a constant value, that is malloc origo. So when giving a pointer to the ptr to idx macro, it is converted into an index in the pages directory, which is an index in the second part of this directory. It returns the index of the element corresponding to the page. Then, pages directory also references the PG infrastructures for tiny chunks and medium-sized chunks, because the top layer function always overwrites the malloc first value that is set in the pages directory by the bottom layer, and it overwrites it with the address of the PG infrastructure. So if you have a tiny or medium-sized chunks, ptr to idx of the address of the chunk is simply the index in the pages directory of a pointer to the PG infrastructure. Now we will detail malloc and free algorithms. So what malloc does is first perform a concurrent call check to avoid race conditions if someone calls malloc in a signer handler or something. It uses a static variable which is increased when it starts working and which is decreased when it stops working. And if it is already active, if malloc has already been called and has not yet finished its job, when it is called another time, it simply writes a warning and does nothing. Then it calls the internal memory allocator to do the real job. So the internal memory allocator first tests if the chunk is a large chunk or a small chunk. If it is a large chunk, it calls the bottom layer malloc pages function to allocate a number of memory pages. And if it is a tiny or medium-sized chunk, it simply calls the malloc bytes functions that will do the job. First, the bottom layer function, malloc pages, rounds the size up to a multiple of the number of the page size, and looks for a sufficient number of adjacent free pages in the free pages list. So it starts in free list, takes the first region. If it is large enough, it stops, takes this region, or it may reduce the region if the region is too large. If there is a perfect match, is if the region has exactly the size of the region that was required, it is simply removed from the list. The PG free structure is removed from the list, and the address of this region is returned to the caller. Otherwise, if the first match is too large, is larger than the requested size, then the page field of the PG free structure is increased, the size field is decreased, and the address of the region is returned to the caller. At last, if there was no match, new pages are mapped through a call to mmap or through a macro which does a call to mmap, and then the pages directory is updated to reflect the modification. So the element corresponding to the first page is set to malloc first, following elements are set to malloc follow. They were set to malloc free before this operation. Then, if a PG free has been marked for freeing, for example, if areas have been merged, if if a PG free has been marked for freeing, which happens when it becomes useless because the whole region is allocated, then if the PX cache is empty, the PX cache becomes the address of the PG free structure. And if the PX cache is not empty, if it already contains the address of a ready-to-use chunk, then the PG free structure is freed through a call to ifree. Now the malloc bytes function, which does the top layer allocation. First, it makes sure that the size is at least 16 bytes and finds G such that the size is equal to 1 shifted G times on the left. And if the pages directory does not reference any list, any page containing 3 chunks of the right size, then they create a new page by calling the malloc made chunks function. And this function maps one page with the bottom layer malloc pages function, tests if the chunks are tiny or medium sized, calls imalloc to allocate a PG infrastructure if necessary, which means if the chunks are medium sized chunks, initializes the PG infrastructure fields, and then updates the pages directory, so it stores the address of the PG infrastructure in the pages directory. Then, back in malloc bytes, it chooses the lowest address free chunk in the associated page, and takes this chunk, puts the bit to 0 in the bits field, and return. The PG infrastructure may be removed from the list if it becomes full of chunks. If no other chunk is available, the page is removed from the list. And that's all for malloc bytes. Now, the free function first performs the same kind of concurrent call checks than malloc, then calls the ifree function to perform the real job. So the ifree function checks the pointers in the beer card memory region, there is no problem. To do this, it simply calls the ptr to idx macro, and if the result is larger than the size of the pages directory, it means we are freeing a junk pointer. Then, if the associated pages directory entry is malloc first, this means that we are freeing a large buffer, so the free pages bottom layer function is called to free the buffer. Otherwise, it is the address of a PG infrastructure, and the free bytes function is called to free this chunk. So the free pages function first performs sanity checks. The pointer must really point to the beginning of a page. To know this, it simply computes it checks the pointer is equal to a multiple of the page size, and if this is the case, it really points to the beginning of a page. It marks the pages as free in the pages directory, so the malloc first is overwritten with the malloc free, and consecutive malloc follow elements are overwritten with the malloc free. Then it makes sure the page cache is not empty. If it is empty, it is allocated with a call to imalloc. It inserts the free area in the free list with two constraints. First, it must enforce its sorting policy, because it is sorted in increasing page field order. And then it performs area merges if possible. So if the freed region is located straight after another free region, simply the two areas are merged, and only one PG free structure will be used for both areas. And if the region is tried before another free region, there is another area merged. Possibly, the free pages functions try to unmap pages in the break region. It is possible if the end of the break region is full of free pages that are not in use. If more than 16 pages are not in use at the end of the break region, they are given back to the kernel. And if two merges were performed, one of the PG free structures that was referencing one of the pages is becoming useless, because you have one PG free structure to reference the three areas, and you had two PG free structures before to reference two free areas. So when this happens, we get rid of a PG free structure through a call to ifree. Now the free bytes function first performs sanity checks, which is the pointer must really point to the beginning of a chunk, not in the middle of a chunk or something, and that the chunk is not already free. If one of these checks fails, the function simply does nothing and writes a warning message on the screen. Then the chunk is marked as free in the bits field, and if the page was full of allocated chunks, it is reinserted in the pages directory, because it had been removed from the list. It is inserted in the list again to reflect there are available chunks in the page. Of course, this operation enforcing the sorting policy of the list. Then the realloc function, I won't completely detail the algorithm, but the basic idea is that it tries to use the same place in memory If the chunk is a large chunk and the newly requested size doesn't change the number of required memory pages, then the same area is used and nothing is done. If the chunk is a tiny or medium-sized chunk, then if the operation doesn't change the category of chunks, again nothing is done. Otherwise, a new chunk is allocated with a call to imalloc. Data is copied from one chunk to the other with a memcopy, and the former chunk is freed with a call to ifree. Now, it's time to play with sample exploitation techniques. So, I first recall a few parameters that may be useful. We will work on the Intel architecture that is well known. First, the PG infrastructures on Intel architecture are 16 bytes plus the size of the bits field. So, in most cases, it will be 32 bytes chunks that will handle these structures. In fact, all PG infrastructures except PG infrastructures describing 48 bytes pages are in 32 bytes chunks. So 32 bytes chunks are really important on the Intel architecture. Another reason why it is important is that PG3 structures occupy 20 bytes. So they are also stored in 32 bytes chunks. And then the page size is 4 kilobytes, and you can have 128 chunks in a 32 bytes page. In a 32 bytes chunks page, sorry. So a simple program simply reads a line from standard input, takes the first character of this line as an argument and operation to perform. If this argument is a plus, then a malloc will be performed, a malloc whose size is controlled by the rest of the line. And if the operation is a minus, the corresponding address will be freed, address which is also given by the rest of the line. So it calls the vol inside function with the operation and the rest of the line converted into an integer. So we will look at different implementation of the vol inside function. First implementation, it simply allocates an attacker-specified size, a chunk, and reads a new string from standard input in this chunk. So we have a basic heap-based buffer overflow, and then if the operation is a minus, it simply frees an arbitrary address. So, any ideas to exploit this vulnerability? Okay, so here is a simple exploitation technique. First, you have the initial heap state. The beginning of the heap contains the PG infrastructure describing the first memory page, and the first memory page is necessarily a 32 bytes chunks page because malloc initialization function always sets the PX cache and allocates 32 bytes to store the PX cache in this chunk. So you necessarily have a 32 bytes chunks page. We can allocate a dummy chunk, whose content doesn't matter, and then force the allocation of a 2 kilobytes chunks page. So you have a PG infrastructure that will be located right after our dummy chunk, and another dummy chunk in a 2 kilobytes chunks page. Then if we free the first dummy chunk, we have a gap before the PG infrastructure. We can allocate the 32 bytes chunks again and simply overwrite it to also overwrite the PG infrastructure, which is what happens. Then, next call to the malloc function, which allocates a 2 kilobytes chunk, will return whatever you want, if you have overwritten the PG infrastructure the proper way. To override this structure, you have to vary certain fields. So the next allocated chunk is located at the page address plus n times one shifted shift time on the left, where page and shift are the corresponding fields of the PG infrastructure, and where n depends on the bits field. So the only fields that really matter are the page field, the shift field, and the bits field. Size may matter in certain configuration because the allocator is partly configurable through environment variable but this is not the default. And other fields do not matter. Another implementation of the vulnerable function only has an off by 1 because it reads from standard input the proper number of bytes, the size of the chunk that has been allocated, and then it zero terminates the string. So we have an off by 1, and the off byte is a null byte. So to exploit the vulnerability, it will be quite more complicated because we can't simply overwrite a malloc structure because we only have the off by 1. And what we have to know is that the field that will be overwritten is the next field. So we will overwrite the lowest order byte of the next field of a PG infrastructure, or we can overwrite a PG3 structure. It will also be its next field. PG3 structures are not easy to overwrite because most of the time when you specify an arbitrary address in a PG3 structure, when trying to access the memory and trying to register the fake page in the pages directory, most of the time malloc will segfault because the page field that you will have chosen will not be in the heap, it will be the stack or the GOT or something, but most of the time it will be out of the pages directory, so this will fail. So we simply concentrate on overwriting PG infrastructures. So always the same thing, we first allocate a dummy 32 bytes chunk, then allocate a 2 kilobytes page, we complete the page is complete and the PG infrastructure has been stored after the dummy chunk. Then if we again freeze the dummy chunk and overwrite it, we will overwrite the next field of the PG infrastructure with a 0, but the problem is that the next field is already 0 because the list is empty and contains only the list contained only one element and is now empty because you have no free 2 kilobytes chunks available. So we need to create a gap so that the list of 2 kilobytes chunks page will have 2 elements, and we will try to overwrite the next field of its first structure. So we also need to leak some bytes for reasons that will be explained later. Then create a new 2 kilobytes chunks page. This allocates a new PG infrastructure to handle the page. Create the gap by freeing a chunk in the first 2 kilobytes chunks page. Now that we have a gap, the first PG infrastructure points to the second PG infrastructure, so its next field is no longer 0, and overwriting it may be useful. So we can free the dummy chunk, allocate it again and overwrite it, and now the next field has been broken and points somewhere else. Where does it point? It was pointing to the second PG infrastructure, whose low order bytes, if you count, was set to 0x20, and now it is set to 0, so it points to the dummy chunk that was allocated just right before the second PG infrastructure. So if you have stored a fake PG infrastructure in this chunk, again malloc will return whatever you want next time it is called. So you can override the GOT or the stack or whatever you want. Now, to have an example of a real flow, I will speak about the CVS flow that was reported a few months ago by Stefan Esser in a VulnWatch posting. He proposed an exploitation technique that is based mostly on CVS, on the deep knowledge of CVS, so of the inner workings of the server, and does not require a very important knowledge of the BSD malloc locator. The technique I propose here is different. It relies on a deep knowledge of the allocator and no knowledge at all, or quite no knowledge at all, of the CVS server. So the main server loop first reads a line from the network with a few arguments, and this line is duplicated in a buffer that is dynamically allocated, and the address of this buffer is returned in the CMD parameter that will be freed later. And depending on what the line contains, on the first word on this line, a function is called whose name is server underscore something. This something depends on what is this first word, and the rest of the line is given as an argument to this function. So server something functions are attacker controlled. Their arguments are attacker controlled. The vulnerability now comes from the serve directory function, which receives an argument that is controlled by the attacker. And what this function does is read another line from the network and call another function, the dir switch function, with two arguments that are again attacker controlled. Then the line that is read from the network is freed, and it continues. The flow is in the dir switch function. First, it checks the static variable dir name, that is a character pointer, is not null. If it is not null, this static pointer is freed. Then the directory length is computed. This directory length depends on what the attacker has sent, so the dirlen variable is controlled by the attacker. And if the directory that the attacker has sent to the function has a certain format, the function exits because it is an error. It must not be terminated by a slash or something. So in this case, an error is allocated, an error string is allocated, and the function returns. If this is not the case, a malloc is called to store the directory name, and this malloc, the size of this malloc is attacker controlled, because the dirlen is controlled by the attacker when the dir switch function is called, and the srv temp dir variable whose length is computed may be controlled by another command in the server. So the flow is that simply, if we allocate a chunk, if we send a proper variable, a proper directory name, the dir name variable will be allocated, and then if we send another directory name, which has an improper format, a call will be made to free dir name, and dir name will not be set to null. So if we again send another malformed string, the dir name variable will again be freed, but it is not allocated. So simply, you have a multiple free. You can free the variable anytime you want. A few things we need to know about CVS buffer handling is that data coming from the network is stored in 4 kilobytes buffers, allocated 16 at a time.